Hello and welcome everybody to the June 2021 technical presentation brought to you by IEEE MTTS Santa Clara Valley San Francisco Joint Chapter known as MTTS-CV. My name is Utkarsh Unikrishna. I'm the chairman of this chapter and would like to welcome you all to this talk. We are very fortunate to have with us a very accomplished academic and researcher, Dr. Harish Krishnaswamy, who is the Associate Professor of Electrical Engineering and also Director of the Cosmic Lab at Columbia University in New York. The talk he'll be presenting here, the title of which is Confluence of Electromagnetics, Circuits and Systems Enables the Third Wireless Revolution. I'm pretty sure it's going to be a pretty interesting talk. So before we go on to that itself, a couple of slides I want to present. As you all know, it's IMS time, and we've already had the live event in Atlanta. This time it's going to be hybrid, and then the virtual event is pending, which will be 20 to 25th of June. So if you guys haven't had a chance to check out the website and see all the different virtual events, there's going to be a virtual exhibition. There's going to be a bunch of different workshops and other presentations. So if you haven't had a chance to take a look at this, please do so at ims-ieee.org. We'll be sending this link out as part of our post-event engagement as well. But I strongly recommend you go take a look at all the exciting stuff that's available at the virtual event. So with that, we will go on to the agenda for today. And for presenting this, I would like to call upon our treasurer, Mr. Than Tu, to kind of walk through the next few slides.
Okay, so for the agenda today really is that, so for right now, we are not meeting in person. So this meeting is being recorded and it's broadcasted live on Zoom. Link to this recorded video will be sent out to the registrants at a later time. In order to preserve bandwidth, please keep cameras off and microphone muted, and also to help with the background noise. If you need to ask a question, please use the raise hand reaction button, and then one of us will unmute you and allow you to ask a question. Please also make sure that your display's name in Zoom matches the one that you usually registered. That way we can identify you correctly. Next slide. In terms of the current situation, we are moving into a more liberal environment, but for now, all our meetings are still on Zoom and not in person. We're hoping to change that in the future, but even for next month, we'll continue with the online format until better arrangements are made. Next slide. The focus of the IEEE is to advance technology for humanity. The IEEE and its members inspire a global community through highly cited publication, conferences, technology standards, and professionals and educational activities. The Microwave Theory and Technique Society focus on the theory and application of radio frequency, guided wave, and wireless technologies. Please support us by becoming a member. And we have provided the link down here through the IEEE.org. Please join the membership there and also join the MTT organization. This list, the officer for the chapter, as mentioned before, as introduced before, Utkarsh is the chairman. Vice chair is Thomas K. The secretary is Venkata, and myself, Than Tu. I'm the treasurer.
Okay, thanks, Than. For the next slide, I just want to mention that this talk is a joint talk between the local Santa Clara Valley chapters of MTTS and the Circuits and Systems Society. So CAS SCV chapter officer list is presented here. These are the four main officers. The chair is Dr. Amit Jha, who I think is here today in the list of attendees. I see his name. Welcome, Amit. And the vice chair is George Chen. Treasurer is Heymin Jin, and Secretary is Zi Chen. There are other officers also, industry liaisons, webmasters, and so on. So yeah, just wanted to mention that. So to present our speaker, Dr. Harish Krishnaswamy, who is a senior member IEEE, received his BTech degree in electrical engineering from IIT Madras in Chennai, India in 2001, and the master's and PhD degrees in the same from the University of Southern California in Los Angeles, CA in 2003 and 2009, respectively. In 2009, he joined the EE department of Columbia University in New York, where he's currently an associate professor and director of the Columbia High Speed and Millimeter Wave IC Lab, COSMIC. In 2017, he co-founded Mixcom in Chatham, New Jersey, a venture-backed startup to commercialize COSMIC Lab's advanced wireless research. His research interests include integrated devices, circuits, and systems for a variety of RF, millimeter wave, and sub-millimeter wave applications. Dr. Krishnaswamy was a recipient of the IEEE International Solid State Circuits Conference Lewis Winner Award for Outstanding Paper in 2007, the Best Thesis in Experimental Research Award from the USB Viterbi School of Engineering 2009, and the DARPA Young Faculty Award in 2011, amongst many other awards. He has been a member of the Technical Program Committee of various conferences, including the IEEE International Solid State Circuits Conference since 2015, and the IEEE Radio Frequency Integrated Circuit Symposium since 2013. He has also served as a distinguished lecturer for the IEEE Solid State Circuit Society and is a member of the DARPA Microelectronics Exploratory Council. A little bit of information about the talk itself. Integrated circuits have fueled revolutions that have deeply impacted modern society, including the computing revolution, the internet, and the first two wireless revolutions. We are at the dawn of the third wireless revolution, which can be called the wireless mobile reality revolution. Over the next 15 years, new wireless paradigms spanning from radio frequencies to millimeter waves and terahertz will change the way in which we interact with the real world through applications such as mobile, virtual, and augmented reality, vision quality imaging, gesture recognition, and bio and material sensing. This talk will describe research along these lines from the COSMIC Lab at Columbia University, including a new approach to breaking Lorentz reciprocity to engineer high-performance non-reciprocal components such as gyrators, isolators, and circulators, and how these integrated non-reciprocal circulators enable practical integrated full-duplex wireless radios. It will describe the FlexIcon project at Columbia, which is taking a holistic and cross-layer view of full-duplex networks from the physical layer to the networking layer. It will also briefly touch upon other work from the COSMIC Lab in the same vein related to high-power, high-efficiency millimeter wave radios, MIMO radios, optoelectronic LiDARs, and city-scale wireless testbeds. So with that, we will hand over to the speaker. So I'll stop sharing. All yours, Harish.
Perfect. Thank you very much for inviting me for this monthly talk. And once again, let me say that you guys do a phenomenal job in putting these things together, extremely well attended. So it's a privilege for me to be here. Are the slides coming through okay?
Yes, they are.
Okay, perfect. So this talk essentially is covering how the confluence of electromagnetics circuits and systems will enable the third wireless revolution. And so essentially, what do I mean by that? So let me start by kind of motivating what these wireless revolutions are in my mind, and then sort of get to the technical material regarding how new wireless paradigms are being enabled by this confluence of electromagnetic circuits and systems. So I think it's no surprise to anybody, especially people attending this talk, that a big portion of the big data revolution is the wireless aspect of it, where because there's so much data being generated and consumed, the burden on wireless networks to transfer this data and move it around is ever increasing. Cisco every year puts out a survey of what global wireless traffic looks like and will look like for the future. This snapshot's actually dated at this point. It's at least 4 years old. But what you can see here is that really wireless capacity increases at an exponential rate year on year. And really what is driving this is the fact that we've transitioned to a situation where our personal computing devices are now dominantly smartphones and tablets as opposed to desktops and laptops, which is what they used to be, even 5-10 years ago. And on these mobile personal computing devices, we are really starting to stream video, things like that, that really dominate the mobile data usage. And so that really sort of segues into this concept of the three wireless revolutions, that, the two that we have seen and the third that we are at the cusp of. So, I like to think of the first wireless revolution as the 1990s to about 2000. And I think of this as the mobile wireless communication revolution, where at this time, technology took us to a place where everyone had a cell phone in their hand and could instantaneously be connected to anybody else across the world. And this was sort of roughly contemporaneous with 1G and 2G technologies rolling out. The second wireless data revolution I like to think of as roughly running from about 2000 to maybe present day, which I like to think of as the mobile wireless data revolution, where essentially mobile technology reached that level of maturity and that level of capacity where one could get on the internet instantaneously from our handheld devices. And so one instantly had access to a wealth of data over the internet. And this was roughly contemporaneous with the rollout of 3G and 4G technologies that brought that capacity to us. And so that brings us to where we are going with 5G, which of course we're in the thick of today, and future 6G technologies. What will that bring for us? So I really think the next 15 years will be the era of mobile wireless reality. And what I mean by that is that wireless will now allow us to interact with the real world in different ways. And so this means essentially things like virtual reality, augmented reality, gesture recognition, vision level sensing, etc. And so essentially it'll allow us to kind of connect to the real world in new and different ways. And this will be transformational in how we experience the world and the amount of information that we essentially have access to. Because certainly the amount of information that is contained in the real world in things like the positions of objects, the materials that they are made of, how these objects move around, is exponentially more than what is actually on the internet today. But what will really enable this next wireless revolution and what underpins 5G today, as well as future 6G technologies, is emerging wireless paradigms. And so we already know that 5G is really embracing millimeter wave mobile wireless, spectrum beyond 30 gigahertz, or maybe 20 gigahertz loosely defined. Also, it's of course embracing massive MIMO, where we use a multitude of antennas at the base station to simultaneously establish multiple links with multiple users at the same time, thus increasing aggregate network capacity. But then, similar to those, there are other wireless paradigms that have not yet made their way into practical networks yet, but potentially underpin future wireless generations such as 6G. And so one example is, of course, full-duplex wireless, which this talk will cover in some detail. Another example is spatial modulation, which still remains in the realm of theoretical investigation, but is yet to be reduced to practice. Of course, there's a lot of interest in terahertz technology, or beyond 100 gigahertz loosely defined. And so these next generation wireless paradigms will really enable that next increase in data capacity for 5G and 6G. But one thing about these emerging wireless paradigms is that they force us to kind of re-examine how we build wireless systems. And that's really been at the root of the philosophy of the research that is explored in my lab at Columbia University. And so really my lab essentially likes to work at the intersection of applied physics and electromagnetics, integrated circuits, and communication systems. And certainly the center of gravity of what we do lies in the middle, in the integrated circuit realm. We build chips and demonstrate practical systems, but we like to take inspiration from new advances that are happening in the world of physics and electromagnetics. And we also like to take inspiration from the requirements of emerging communication systems and understand what they demand from the hardware layer. So with that, maybe let me pause really quickly to see if you folks have any questions regarding the broad overview. And then, if there are, after addressing those questions, we can sort of go into some of the detailed technical portions of the talk.
So folks, as always, to pose a question, use the reaction button and hit the reaction button and then just hit raise hand and we'll take your questions. I think we might be good to proceed.
Okay, sounds good. So this talk is essentially divided into sections where we talk about some advances in the realm of electromagnetics and physics, and then we talk about how they may be brought to bear for wireless systems with an emphasis on MIMO and full duplex. And then towards the end, we will talk about emerging applications in the medical realm, in the quantum realm, etc. And really, of course, what ties everything together is circuits, and that's of course the platform in which we build practical demonstrators for this. So in the realm of electromagnetics, one of the main focal points for my group has been exploring the role of time variance in electromagnetics. So a time variant electromagnetic system or a time varying circuit is one where there's some parameter of the circuit or the electromagnetic system that is modulated in time. So that could be the value of a capacitor in a circuit, or it could be the permittivity of a medium or the permeability of a medium. It could be the use of switches in the circuit, where a switch is essentially a time varying resistor. And what's interesting about time variance, which really has grown as a research direction over the last 5 to 10 years, is that it can be used to overcome fundamental limitations associated with time invariant circuits or electromagnetics. And some examples of these fundamental limits that we've been looking to overcome is reciprocity, so building of non-reciprocal circuits and systems, overcoming the delay bandwidth size trade-off, etc. And so we'll talk about these in some detail. And so let's start with integrated non-reciprocal components. And so to understand this direction of research, let's ask the question, what is reciprocity? And so reciprocity is a fundamental concept that underpins many different kinds of wave propagation, whether it's electromagnetic waves or sound waves or acoustic waves. It underpins thermodynamics. And what it essentially says is that the nature of wave propagation remains unchanged if you interchange the source and the observer. Or said another way, waves travel in the same manner in forward and reverse directions, very loosely speaking. Now, if you break reciprocity, then essentially you're trying to realize a system where the forward traveling of a wave is different from the way it would travel in the reverse direction. And so one example of a component that is non-reciprocal is a gyrator, which is a component that has a different phase shift in the forward and reverse directions, where typically that phase difference is 180 degrees, where you maybe get plus 90 degrees in the forward direction and minus 90 degrees in the reverse direction. Another example of a non-reciprocal component is an isolator, which allows signals to travel in the forward direction, but does not allow any wave propagation in the reverse direction. And another example is the circulator, which is a 3-port component where signals can travel in one direction, for instance, clockwise from one port to the next, but in the reverse direction, signals cannot propagate at all. And these types of non-reciprocal components find widespread use in wireless systems today. So an isolator is typically used in a high power base station at the output of a power amplifier, so that the signal from the power amplifier can be transmitted to the antenna. But if there is any reflection at the antenna, it cannot come back to the power amplifier. And so this actually prevents the power amplifier from seeing impedance variations due to a change in the electromagnetic environment of the antenna. Circulators are actually used in full duplex wireless systems where they allow a transmitter and a receiver to essentially communicate with a single antenna at the same time, where you can have a signal travel from the transmitter to the antenna, but any incoming signal at the antenna won't go back to the transmitter. It will actually circulate to the receiver. These types of circulators are also useful in other simultaneous transmit and receive applications, for instance, radar. So FMCW radar operates in simultaneous transmit and receive mode, whether it be for automotive applications or defense applications, and circulators are used there as well. Circulators and isolators are also extensively used in emerging cryogenic quantum computing applications, where they're used to isolate the qubit from the excitation signal, the readout from the excitation signal. And so clearly these are useful components. And so, it's useful to have cost-effective ways of building them. And so, let's understand how we can build these non-reciprocal components. So the fundamental principle of Lorentz reciprocity states that any linear time invariant system with symmetric permittivity and permeability is reciprocal. And so if you want to build something non-reciprocal, you have to violate one of these necessary conditions. And so one way is to use ferrite materials. Ferrite materials are special materials where once you apply a magnetic field, the dipoles inside that material realign, and that results in an asymmetric permeability tensor, and that makes the ferrite material inherently non-reciprocal. And this is, of course, the dominant way in which circulators are built today and isolators are built today. So, extensively, magnetic or ferrite circulators and isolators are available and are used in applications today. In fact, active transistors are also non-reciprocal. So, if you just think about a transistor amplifier, it has gain in the forward direction and isolation in the reverse direction. So that's inherently non-reciprocal. And so the use of active transistors has actually been explored to implement isolators and circulators for many, many years. You can violate linearity. Nonlinear systems can be non-reciprocal if they're combined with some kind of spatial asymmetry. And so this is an approach that has been explored as well. But each of these approaches has a fundamental challenge. So ferrite materials are not integrable in semiconductor processes. And so ferrite non-reciprocal components tend to be bulky external components that are expensive as well. So that's actually driven a lot of interest in building integrated non-reciprocal components, and people have explored both the use of active transistors as well as non-linearity. However, any active transistor is associated with noise and non-linearity. And nonlinear system is, of course, inherently, as the name indicates, nonlinear. And both of these are issues for wireless systems where generally you want low noise and highly linear operation. And so that's why over the last 5 years or so, there has been a lot of interest in violating that last remaining necessary condition, which is time invariance, and to use time variant systems to realize non-reciprocal components. And so there's been work in other groups, including Andrea Alou's group, who formerly at UT Austin and now at the City University of New York, as well as my group in this direction. And so we built actually the first non-reciprocal circulator in a CMOS chip back in 2016 using a circuit called an N-path filter. And this N-path filter is, of course, a circuit that has been very popular in the circuits community for the past 10 years or so. It's essentially a switched capacitor circuit. You have a bunch of switches, capacitors, and a bunch of switches on the other side. These switches kind of turn sequentially on with these low duty cycle clocks. And then the switches on the other side also turn sequentially on as well. And what we found, so the attractiveness of this N-path filter for the circuits community has been that basically by performing switching across a capacitor, one can essentially realize a band pass response at RF at the frequency of the clocks without using any inductors. So just by using switches and capacitors, one can realize a transfer function that looks like an LC second order resonant filter. So it's essentially an inductorless LC resonator, so to speak, with the resonance frequency being the frequency of the clocks. But what we found, which is quite interesting, is that if you phase shift the clocks between the left and the right hand side, then in addition to that LC resonance, you also get a non-reciprocal phase shift, where the phase shift in the forward and the reverse direction is different. If you're phase shifting the clocks by phi, in the forward direction you get plus phi, in the reverse direction you get a phase shift of minus phi. And so you can actually realize a gyrator just by using the switched capacitor circuit if you include a phase shift between the clocks. And using that gyrator, we actually implemented a circulator as well by embedding that switched capacitor gyrator within a transmission line loop. So that was our first work. It was published in Nature Communications in 2016, and it was the first realization of a passive circulator on a silicon chip. Since then, we've been sort of extending this concept further, trying to push various performance metrics, including operation frequency, bandwidth, power handling. And one of the advances since that first work is that we found that if you do this switching across a transmission line as opposed to a capacitor, then you can get very wide bandwidths. And essentially, so what this transmission line is doing is it's kind of delaying the signal by the same amount that these switches are delayed. And so as a result, it significantly enhances the bandwidth across which this gyration is achieved. Where now what happens is in the forward direction, signals enter the transmission line, travel through, they get to the other end. And when they get to the other end, the switches here are closed and they come out. But then when you look at the reverse direction, signals enter this side, travel down the line, get to the other end. But when they get to the other end, because of the phase shift, the cross switches are enabled. And so the signal flips and then comes out. And so essentially what you then have is in the forward direction, you have regular transmission. In the reverse direction, you actually have an extra sign flip. And so you get a transfer function where you have a non-reciprocal phase shift of 180 degrees because of this sign flip that you see here. And you get that non-reciprocal phase shift across actually theoretically infinite bandwidth. And so you significantly enhance the bandwidth of the gyrator. And so with that enhanced bandwidth, what you can do is that you can actually either increase the clock speed and operate this at higher frequencies, or you can use a much lower clock speed and you can essentially use transistors with higher power handling, and you can enhance the linearity. So basically that bandwidth can be used either to achieve higher frequency of operation or to essentially enhance the linearity and power handling. And so using this approach, since then, we've implemented circulators at multiple different frequencies with different power handling. So, these orange dots here were our first works using the NPath approach, which were implemented around 1 gigahertz, and the power handling was in the single digit to tens of milliwatts. Using this new transmission line based architecture, we've implemented circulators that operate at similar frequencies of about 1 gigahertz, but with power handling as high as several watts, so 30 dBm and 34 dBm. We've also, on the other hand, pushed the operating frequency to millimeter waves, where we first implemented a circulator up at 25 gigahertz with maybe about 100 milliwatt of power handling. And then later we demonstrated a circulator up at 60 gigahertz, similarly with 100 milliwatts of power handling. So this architecture has really enabled us to push both linearity and power handling for these circulators. So that was our effort towards breaking reciprocity. Let me talk about now how time variance can allow you to overcome other trade-offs, specifically the delay bandwidth size trade-off. So what is the delay bandwidth size trade-off? So fundamentally, any electromagnetic structure that you build, there is a trade-off between delay and bandwidth. So for instance, if you make a transmission line can have theoretically infinite bandwidth, but it has fundamentally low delay, or at least to get very large delay, you have to use a long length of line. To get more delay within a certain size, you can actually use lumped components. For instance, you can make quasi-distributed transmission lines with lumped L's and C's. And now because of the larger per unit length L and C value, you can get more delay with within a certain area. But the bandwidth of this would be fundamentally limited by the Bragg frequency limit, right? And so you're trading off the delay for bandwidth. And you can also think of this in another context, which is typically how the folks who work in the optical domain think of this, where you can think about a resonator or a resonant cavity, where to get more delay, you need a higher Q from that resonator. So, delay of a resonator is inversely proportional to Q. But then if you use a higher Q to get more delay, then you essentially shrink the bandwidth. And so again, bandwidth and delay, trade off against each other. And so here is where, again, these switched capacitor circuits become very interesting. So historically, people have looked at these N-path circuits in two different regimes. The first regime is one where you have a very large capacitor. Specifically, what large means is that the port impedance times the capacitance, that RC time constant is large compared to the on period of these clocks. And in that regime, you get this, we talked about this before, this second order LC band pass response. So you get an LC response, but without the inductor. And actually, we didn't mention this earlier when we talked about this, but you actually get a comb filter response, meaning you get that LC response not only around the clock frequency, but around every harmonic. On the other hand, there's another regime where the capacitor value is very small, meaning this R times this C is small compared to the on period. And in that regime, this circuit behaves like a sampler. In fact, this type of a sample and hold circuit is extensively used, of course, in ADCs and such. So what we've been exploring is this intermediary regime where this RC product between the port impedance and the capacitor is of the order of the on period of the clocks. And so in that regime, what essentially happens is, if you imagine you have a sine wave, then that sine wave keeps getting stored on these capacitors. Different portions of the sine wave keep getting stored. And then when the switch on the other side is on, that stored charge is released to the output. And so, of course, when it's released, there will be a sort of RC decay kind of response. And so when I look at this output voltage, it sort of has the same envelope as your input signal, but of course, with these, RC decay kind of spikes around it. And so loosely speaking, you get a transfer function from the input to the output, which sort of faithfully or barely kind of tracks the input shape. But interestingly, with a delay that can be controlled by controlling the delay between the left-hand side clock and the right-hand side clock. So you can transmit the signal from the left to the right, but with a programmable delay, which is governed by the delay between the clock on the left and the right-hand side. And so essentially, you're now getting a delay element where the delay element is not dependent on this resistor or capacitor value, but is more controlled by the clock. And so when you look at the S parameters of a structure like this actually looks like a broadband delay where you essentially have a fairly broadband magnitude response and you can get fairly decent matching, but you now have a delay which is controlled by the clock delay. And so you get a group delay in the forward direction, which is this brown line. And what's interesting is also that there will be a delay in the reverse direction as well, but that will be determined by the delay when I look at pink versus green, right? So, if I have 3t over 4 delay in the forward direction, and the reverse direction will look like actually t over 4, which is whatever is left in that period. So the delay is actually interestingly non-reciprocal. But what's critical about this structure is because we've decoupled the transfer of the signal in the bandwidth of it and the delay, it turns out that for this structure, the delay bandwidth product is actually proportional to the number of paths that you use. And so the more the number of parallel paths, the more you can increase the delay bandwidth product. And it actually defeats the fundamental delay bandwidth limitation of traditional LTI circuits. The other aspect about this is that we call this kind of structure, this kind of delay element, a quasi-electrostatic delay. And the reason is when you think about a traditional LC transmission line and as signals propagate through it, the energy that is stored in the inductor and the capacitor tend to be equal. And so you have equal energy being stored in magnetic and electric forms. But when you think about this switched capacitor structure, and typically we add some extra inductance on the left and right, and that extra inductance gives us some extra matching and increases the bandwidth a little bit. For this type of a structure, dominantly the energy is actually stored in the capacitors. And there's very little energy stored in these very small inductors. In fact, for some very typical delay lines that we build, it's actually 25 times more energy that's stored in the capacitor. It's largely a switched capacitor structure rather than a true electric and magnetic transmission line. And so that's why we call this quasi-electrostatic wave propagation. And because it's mostly capacitors which can be compact, you can actually shrink the size of a delay line by as much as 100x to 1000x because the inductors are extremely small. And so we've implemented delay elements to demonstrate this concept. I'm showing one here, and so these delay elements basically give you a significantly they're anywhere from 100 to 1000 times smaller than traditional delay elements, whether you implement them as lumped LC delay elements or active delays or PCB based delays. And the other thing about these delay elements is that they are also reconfigurable. So of course you can change the amount of delay that you get by changing the clock phase shift. And of course, separately, you can change the impedance of the line also by changing the capacitance that is being switched across. And so the other nice thing about these delay lines is you can reconfigure characteristic impedance and delay independent of each other, something that you cannot do in a traditional transmission line. And so we use this idea to actually build a 4-port network that you see here on the left-hand side, which can be reconfigured between multiple functionalities: a rat race coupler, a branch line coupler, and a 3-port circulator. And so just by changing the modulation clock of these delay elements, the amount of delay between the left and the right hand side, and hence the phase shift, and by reconfiguring the capacitor value, you can go from a rat race coupler to a branch line coupler to an actual 3-port circulator. And so we think of this as sort of a Swiss Army knife of microwave passive components, where there's one device that you can just change the clocking and it will basically change from a rat race coupler to a branch line coupler to a 3-port circulator. And in addition, because these are broadband delay lines, you can also shift the center frequency around by a factor of 6.
Professor?
Yeah.
This
Let me
is
stop. Yeah.
Okay. It might be a good time to allow for some questions. If
Yeah.
I have a question or two myself, while others may want to raise their hand. We have a question from Jehan. I'll go to unmute. Let's see.
Good morning, sir. Sir, my question is revolving about the behavior of the switches, because usually an ideal switch in electronics is not always possible. You'll have leakage, and that timing of that delay would also depend on another circuit, maybe like a PLL or something, to ensure the time difference between the green and the pink switches are done perfectly. So is there a inherent limitation from the electronic side as we go higher and higher to these higher frequencies?
Yeah, no, that's a great question. So in general, I will say that in multiple dimensions, these types of time varying circuits, they shift the burden to the clocks, right? In the sense that, for instance, the delay between the left and the right hand side has to be a certain precise value, right? For some of these circulators, for instance, here, what happens is that if you think about this this switch delay line structure, the delay between the left and the right hand side has to match the delay of these transmission lines for everything to work correctly. Otherwise, when you get to the other side, the switches may not have switched correctly and so on. And so what typically ends up happening is that if you analyze these circuits for their performance under, let's say, timing errors, so you can look at, phase errors in the clocks and so on. So that will ultimately limit metrics like isolation, insertion loss, and so on and so forth. The good news is they tend to have sort of a gradual response. So it's not like performance falls off a cliff, but for very typical types of delay errors that you see in on-chip circuits, you might be limited to about 30 dB of isolation or something like that. And of course, even traditional ferrite circulators or other kinds of circulators have other mechanisms that limit their isolation as well. And the other thing I would say about things like timing errors is that's the kind of thing that integrated circuits does very well, where you can calibrate that kind of timing error out, right? Where you can have like a little programmable delay in the clock path, and you can use that to calibrate isolation and so on.
Okay, we have another question from Venkata.
Yeah. Hi, hello, Professor. My name is Venkata. Yeah, you showed a slide where your group has demonstrated various projects where there was improvements in terms of the bandwidth, the speed versus the power capacity, right? Could you talk about how are these improvements coming and what is the role of the technology?
That's a great question. Yeah, that's a great question. So I would say these improvements that we showed, we're getting to higher frequencies and we're getting to higher power handling at the same frequency. These are coming from architecture, right? So these two works here in the star, or these two works here in the green. These are all coming from this transmission line based architecture as opposed to a switched capacitor. And so they are allowing us to get higher power handling or operating frequency. That being said, of course, technology will always, so that's another benefit of these switch type circuits, right? Switches get better as CMOS technology scales, while active circuits don't necessarily get better, right? And so these types of circuits also in general benefit more from technology scaling, where a switch with lower on resistance or lower parasitic capacitance will allow these circuits to perform better.
Okay, I'd like to ask a question, Professor.
Yep.
I didn't follow why the transmission line approach allows for higher power. I think you were just showing that.
Yeah, I think I passed that very quickly. So what the transmission line approach does is that, so in the previous case, when you have the switched capacitor, so the gyration happens purely at the clock frequency. Okay. And so this whole circulator operates in a narrow band around the clock frequency. Once you move to the switch transmission line approach, the gyrator is actually completely broadband. And so it works at any frequency, not just the frequency of the clocks. Right? And so what that means is that you've decoupled the operating frequency from the clock frequency. And so what you can then do is that you can use a faster clock, and that helps you to get the that helps you to go to higher frequencies of operation. Or you can use a slower clock. Once you use a slower clock, you can use transistors with higher power handling. So for instance, you can use like a 180 nanometer RF-SOI process as opposed to 65 to 45.
I got it. So it's the fact that you've got us, the slow allows you to use a higher power handling switch technology.
Exactly.
Is that right? Okay. One other quick thing, you had it on another slide. You mentioned the characteristic impedance on these structures that have a tuning L on the input and output, and then are otherwise, I guess, multi-phase.
Yeah.
You mentioned a characteristic impedance. I'm wondering the definition of that. And then I'm sorry, but I have a third question I want to get out quickly, which is, well, escape my mind for a second here, but if you could explain, the characteristic impedance, I know what the other question is. I'm concerned about the delay modulation, because you're showing you're not showing a full sort of clock, non-overlapping clock, which I wonder what I mean by that is there's not somewhere there's not a phase on, at least in your cartoon explanation. And I'm wondering about losses, right? If there are fundamental loss limits, which is kind of that's probably the more important question. Because on this one, I mean, we like to, as microwave engineers, preserve every ounce of energy available from the source, and obviously you would like to have a phase on all the time, somewhere.
Yeah, absolutely. So with regard to loss, so the way that these switched capacitor circuits work is, let's say that you have 4 paths, right? And so then, these 4 clocks controlling the 4 switches, they would each be on 25% of the time. So the clocks would have 25% duty cycle. And so the first quarter period, the first switch would be on, and this signal would be dumped onto the capacitor. Then in the next 25%, this switch would be on and would be dumped onto the capacitor. And so there's always on the left-hand side 1 switch on. And so you never reflect the input signal, because it's, if something's on, that none of the switches are, there's no point where none of the switches are on, are off, right? And the same is true for the right-hand side, but there might be a delay between the left and the right, and that's governs, so it's like you're catching the signal and you catch all of it because all the switches are on at one point or the other, but then you release later, although you're always releasing as well, because there's always 1 green switch on at a time.
But that means your release has to be within the total period.
Yeah, exactly. So 1 period is the upper bound of the delay that you can impart, right? Because when you exceed a period, then it's actually like you're going back to 0 delay.
Yeah. Okay. Got it. So you had a characteristic impedance definition in the circulator. What is that?
Yeah, so the characteristic impedance of this transmission line, it's actually, sort of deriving it, I can refer you to some of we have a paper in Physical Review X, which talks about how this whole structure behaves. But basically, it's related to 1 over Fc, where F is the frequency at which you switch, and C is the capacitance, basically. And so, these little inductors here that we add, they're actually very small in value. You can even do without them. They just give you a little bit of an extra bandwidth enhancement, but they don't set the characteristic impedance. It's largely governed by 1 over Fc, where F is the clock frequency and C is the capacitance. And so that way you can change capacitance, and that changes the clock frequency. That changes the characteristic impedance, basically.
Okay. All right. Thank you.
Sure. Just wanted to, before we go on forward. Just a
question, if I may.
Okay. Oh no, absolutely no problem. But I just want to double check about time. So do we have a hard stop, or what is the recommended stop time? Can we go ahead?
There is no hard stop. We can overshoot by a little bit if there are questions, and it looks like there will be probably more questions. So we are good on time. Yeah.
Okay, sounds good.
As long as you're good on it.
Yeah. Oh yeah.
Okay, so I think we're going to take a question from Raisi.
Yes. Hello, Professor. Thank you for the talk. My question is, how much power consumption is for these switches?
Yeah, so that's a great question. So that's one of the things that gets better with technology scaling. And so, we've worked on that. So, again, everything comes down to the clocking, right? And so, the timing has to be accurate. And so, we've worked on analyzing the effect of timing errors and how to calibrate that. Power consumption is another thing. With some of the, we've done work on how to minimize the power consumption in the clock path. Just for one reference point, if I go back to one of these circulators, So I think this one, which was at 34 dBm power handling, I think the clock power consumption was about 30 or 40 milliwatts. So it is possible to make these with a clock power consumption that's a small fraction of the power handling.
So my question is it possible to use these devices in multi-channel beamformers for full duplex communications at millimeter wave?
Yeah, absolutely. So we have looked at how these, to look at full duplex in an array context, right? So I will actually have some stuff about that in a second.
Okay, thank you.
Yeah.
Okay, Sala?
Yes, thank you, Professor, for the presentation. I've got a quick question here. With the process of switching on and off the one of the end paths, does that introduce discontinuity? And is there any forms of reflections that may occur being unwanted?
Yeah, it's a good question. So ideally, no, right? So if you have the timing all correct, then no. But if the timing is off and there's a portion of time where no switch is on, then the signal for that brief instant will get reflected. And so, yeah, things like that, which is reflections, reduction, insertion loss, finite isolation, all of these things happen if there are timing errors. And so again, the way around that is to kind of have some programmability in the clock delay so that you can tune and adjust that.
Thank you.
So Jehan, did you have another question, or should we go ahead and move on? I think maybe we should hold some questions. I saw another couple hands go up, but maybe we'll take one more question and then allow the professor to go on. Yeah, it looks like if folks are okay with that, we'll just go on and then we'll take another question period at the end, I suppose. I'm sorry, guys. Yeah, I think we better move on. Okay.
Yep. So I'll now show some work on how we combined these two things, which is overcoming delay bandwidth size trade-offs and non-reciprocity. And so it's actually interesting because we showed that if you basically have a switched capacitor circuit with a delay between the left and the right-hand side, you can get a very broadband transfer function. On the other hand, if you kind of switch in a circular fashion, then you can get a circulator behavior. And so if you kind of combine these and have a bunch of switches and then you switch in a helical fashion, turns out you can combine these two things and you can get a very ultra broadband circulator. And so, again, it's in the interest of time, I mean, it's going to be challenging to sort of go through exactly how this circuit works, but essentially it's a switched capacitor circuit as before, but with multiple ports. And so you're switching between these capacitors in different, sections of the clock, but also in each section for one capacitor, you're going around across these different ports. And so it turns out that when you do that, you can actually get a circulator that is completely broadband, meaning it can operate from DC all the way up to a certain frequency. And so we were actually able to implement a circulator in 65 nanometer CMOS that can work from DC to a couple of gigahertz. And so completely broadband within a very small form factor, within as much as 0.2 millimeter squared, because again, it's just switches and capacitors. There's no inductors in the circuit. So it was a circulator that was like about almost 100 to 1,000 times smaller than prior circulators that we ourselves had built, but at the same time, completely broadband, operating from DC to a couple of gigahertz. So with that, let me move to the final thing that I wanted to cover on the physics and electromagnetics side, which is a little bit more of an exotic thing called topological insulators. But it's actually interesting because we were actually able to find some applications for this in practical wireless communications. And so what is a topological insulator? So it's a material that behaves as a conductor on the surface, but in the bulk of it, it's insulating. And so these are sort of new types of materials that people had discovered maybe about 10 years ago, and they've actually sort of drawn a lot of interest in the materials community. And more recently, what people have been doing is they have been building classical analogs of topological insulators for acoustic waves and for electronic waves. So building sort of metamaterials that behave like topological insulators for either acoustic waves or electromagnetic waves. And it turns out that if you sort of implement an array of circulators, a lattice of circulators, then that structure can behave as a topological insulator, meaning it has very interesting ways in which the signals get routed through the lattice. And so we implemented this first topological insulator on a chip, and it's actually in review in Nature, all in a 45 nanometer SOI CMOS process. And what's interesting is because we're using the circulator unit cell that I just described that is completely broadband, it was also the first topological insulator that can operate over an extremely wide bandwidth. And so the way that it works is because, so let's say you have a lattice of 16 circulators, 4x4 lattice, and they're all circulating clockwise. Then what happens is a signal that you put in on one side, because of the way they circulate, always has to travel across the edge and it'll come out from the other corner, for instance. The attractive thing about these topological insulators is they are robust to defects, meaning if something happens and, for instance, one circulator actually breaks, for instance, and the equivalent of that would be some defect in the electronic topological insulator material that was the original discovery in the physics community several years ago, then the signal can sort of still route itself around it because of the way that the circulators circulate. And so you can have sort of robust wave propagation that is immune to defects, and that you still don't get any back reflections from the defects. And then you can also sort of, if you program these circulators where this bottom triangle operates in a clockwise sense while this top triangle operates counterclockwise, then you can engineer these arbitrary domain walls where the signal can travel along any programmable direction, basically. And so you can think of these topological, this kind of a topological metamaterial, if you will, realized as a lattice of circulators, as basically a fabric that can route signals in any way that you want, in an arbitrary way, just based on how you program these circulators. And so we actually demonstrated this on a chip. These are actually, what I'm showing here are measurements. They are measurements from this chip where the color which is depicted on these cells is actually a reflection of the signal strength. And so what we're showing is how the signal propagates for these different conditions of how we've configured these circulators. So that's a little bit about, sort of new concepts in physics and electromagnetics that we've been sort of adapting to circuits. Let me talk a little bit about how these come together in wireless systems. And maybe when we get through this wireless system section, that might be a good section to stop again for questions. And so a lot of this will focus on full duplex radios. And so full duplex radios are radios that transmit and receive at the same time, as opposed to frequency division duplex radios where you transmit and receive at the same time but at different frequencies, or time division duplex radios where you transmit and receive at the same frequency but at different time slots. And so the idea is that, of course, if you can transmit and receive at the same time at the same frequency, then you can theoretically double network capacity immediately in the physical layer. The challenge, though, is the tremendous self-interference from the transmitter to the receiver. So now you have a significant transmitter signal leaking to the receiver, either through the antenna interface or because of reflections off of nearby objects. And that can now desensitize your receiver because it's at the same frequency as your receiver, and it's coming in at the same time as your desired signal. And so we now need as much as 100 dB of self-interference cancellation, because that self-interference signal can be that much more powerful than your desired signal. And because the signal appears through these many different leakage paths, whether it's through your antenna interface or because of these environmental reflections, you end up needing a canceller that can replicate that self-interference channel. And so you typically need large delays in this canceller that essentially replicates the wireless channel that you're trying to cancel. And so, we've actually studied what is required for cancellation just by taking a circulator and an antenna, measuring the self-interference channel, and then trying to see how the canceller needs to look. And so you end up needing cancellers with many tens of nanoseconds of delay in them, and also very fine resolution. So many taps with fine delay resolution, so that you can exactly replicate the self-interference channel and cancel the leakage signal. And so how do you build these cancellers? So there are two ways to do it. One is by having what's called a time domain canceller, where you have multiple delays in the cancellation path and you have programmable weights on each of those taps. And so by programming the weights on each of these delays, you can sort of create the same response as your self-interference channel. Essentially, this is nothing but an RF FIR filter. And so you can recreate the self-interference channel and cancel it. Or you can do the equivalent in the frequency domain, where you have multiple, let's say, second order filters in the canceller. And by programming the center frequency and Q and amplitude and phase of those filters, again, you can try to recreate the self-interference channel and cancel it. And we've explored, actually, these are papers from my group, we've explored both of these ways. And they're basically duals of each other, whether it's using time delays or by using narrowband filters. And so this first approach, we used end-path filters to realize those filters in the canceller, and we demonstrated this first receiver all the way back in 2015 at ISSCC. It had 2 taps in it. We've also built a couple of generations of these full-duplex receivers where we use our integrated circulators on the on chip as the antenna interface to give you the initial isolation, and then we do some cancellation across it. More recently, we've been using this idea of quasi-electrostatic delay to accomplish time domain cancellation, where we have these switched capacitor circuits that give us delay over wide bandwidth. And then by having some weighting, some gain on top of it, we can essentially now, again, recreate the self-interference channel and get a cancellation. And so again, using the same switched capacitor idea, but rather than using it as a filter, using it essentially as a delay. And so we had this first generation work that was at RFIC Symposium in 2020. At the recent ISSCC in February of this year, we showed a second generation work where once you have these switched capacitor circuits, it opens up a lot of different avenues for you. Where what we are now doing is in that same switched capacitor circuit, in each path, instead of having one capacitor, you can actually have multiple capacitors. And so now what you can do is that in the charging phase from the left, you charge them in parallel. And then in the discharge phase on the right, you stack those capacitors in series. And so now when they're charged in parallel to the same voltage, when you stack them in series, their voltages add up and you get voltage gain. And so by having an additional M capacitors in each path, which are first charged in parallel and then stacked in series, you can get a voltage gain of M. And so you can actually embed some voltage gain in these delays, which you couldn't normally do because it's a passive circuit. And so that gives us actually some gain in the canceller, which can compensate for some loss. and gives us better performance. In fact, the second generation work, which has this capacitive stacking, was actually able to get much higher delay bandwidth product just because of the fact that there was some gain in the circuit. So now sort of moving into the system domain, what's actually important in these full duplex systems is not only do you have to build these cancelers that can cancel the self-interference, you have to also configure those cancelers. You have to find the weights in each of those delay taps or those filter taps, and you have to program them to get high cancellation. And so we've worked on these iterative loops, which basically can iteratively sort of they rely on models that we build on the of the cancelers, and then with fast iteration you can actually converge very quickly to the optimal setting that gives you the best cancellation. So here we're actually seeing that just in 3 iterations, we're able to get very high levels of cancellation, where the original isolation of the circulator was 27 dB. The first iteration gives you 45 dB of cancellation. In the second iteration, you get to almost 60 dB. And then after that, you get very little further improvements. And so, just showing here with this latest chip that was shown at ISSCC 2021, it's a broadband chip that gives you high levels of self-interference cancellation across many different antenna interfaces. We've tried it across a circulator, a magnetic circulator at 450 meg, another magnetic circulator at 800 meg, as well as across some of our own time modulated circulators at 950 megahertz. So let me stop here to see if you folks have any questions before I get to the last, I'd say maybe 15 minutes of the talk.
Yeah, there's a question. Let's see. Where is it? Okay. Raisi?
Yes, thank you. Thank you, Professor. My question is, this idea, this canceller, is it scalable to higher frequencies? Because we need a coupler after that TX, that power amplifier, and it's at a loss to the system and may degrade the efficiency of the power amplifier.
The coupler, that is, right? So
yes.
Yeah, so the degradation in the transmitter efficiency comes down to how much signal you need to couple out. Like, is it a 10 dB coupler, or is it a 20 dB coupler, in which case you're taking out very little signal, or is it a 6 dB coupler, in which case you're actually taking out a decent amount of signal, right? And so that coupler depends on the loss in your canceller, where if you have too much loss in your canceller, then you have to couple out a lot of signal. If you have very little loss in your canceller, then maybe you can take in very little signal. And so certainly as you go towards higher frequencies, reducing the loss of those delay lines becomes more and more critical. Of course, again, technology scaling helps, because all of these circuits get better if the switch quality is better, basically, if there's less parasitics associated with the switch. And so, we are sort of currently working on, getting to higher frequencies. By higher, I mean up to about 6 gigahertz or thereabouts. When you get to millimeter waves, there's another aspect, which is just as you go to higher frequencies, the amount of delay that you need is less, right? Because at millimeter waves, you're not going to get reflections from far off objects, just because the signal itself will die, right? So there is this sense that you need more delay at RF and that you need less delay at millimeter wave, and that should actually help in terms of loss and hence coupler performance.
Yes, but what I meant is the loss of the coupler, because the TX, I mean the signal from the power amplifier, has to go through that coupler from the through port.
Oh,
I'm not talking about the coupler.
Yeah,
yes.
Parasitic loss of the coupler, right? So actually, that's where sort of an integrated implementation can help you. So when you can integrate the TX on the same chip, you don't necessarily need sort of a microwave coupler, which has sort of, like long transmission lines and the through path and so on. So what a lot of people do in these integrated implementations is you can just have a capacitive coupler, meaning have a capacitor that just taps the signal from the output of the transmitter. And the smaller the value of the capacitor, the smaller is the signal that is tapped. Of course, it's not something that has a matched coupled port, right? So the coupled port actually looks capacitive. But again, if you're interfacing with these switched capacitor circuits, that might still be fine. And so that allows you to minimize the through loss. And this, people have done this even at millimeter wave, which is just, couple out with a capacitor as opposed to sort of a traditional microwave coupler.
Okay, so we have a question from Sala.
Yes, I think that my question is probably in the same line as the person who asked before me. Would you place this in line with the signal path? There is losses, and I noticed that the LNA would probably see some of that loss. So would you think that there'd be an impact on overall noise figure of the system? That's one question. And then the other that I'd like to follow up on that. I know that you've mentioned that the size of the ring can be reduced quite considerably and fit into a very small place. I'd like to actually make it the opposite way, make it bigger, and perhaps put most of the supporting circuitries in the middle. Would there be any interference to the transmission lines, more in line with the way that one would build a rotary ring, also like a Mobius ring?
Right. So on the first part, which is, the losses associated with any of this stuff, which is a circulator or a canceller and so on. So certainly, they will introduce some losses, right? And so a lot of these full duplex transceivers are spec'd by how much the noise figure increases under full duplex operation, right? And so, we've been sort of, in our initial works, the noise figure increase was more. Nowadays, we're down to sort of the 1 to 2 dB increase in noise figure, where, maybe you start off with a 3 to 4 dB receiver, and that jumps up to something like, 5 to 6 dB under full duplex operation, right? So that is certainly a concern. And that eats away into the 2x argument about improvement in capacity, right? Because if you transmit and receive at the same time, it's 2x, but if you lose a little bit of SNR because of the noise figure increase, then that eats away into the 2x, right?
Yes.
Yeah, so there's been work, actually my collaborators have looked at the network level, how much do you practically get? And people have shown that, you can get 1.6x, 1.8x, and so on, even when you factor in. So there's a lot of things to be factored in. The noise figure increase is one, the increased power consumption is the other, and so on and so forth. So yeah, it definitely eats away into the 2x. But I wouldn't say that it sort of just completely does away with the 2x. I mean, you can read some of the system level papers that show how to get something like 1.8x or something like that out of the network, even if the noise figure increases. Regards to how you build it and putting stuff in between, yeah, for sure you can do that, right? I mean, there's been, generally speaking, a lot of work on how to put things underneath inductors, underneath transmission lines, in between them. And so all of those things can be exploited to further miniaturize the circuit.
Thank you.
Akash?
Thanks, Tom. So Harish, a quick question about the canceller that you have. I think you mentioned that it contains a programmable delay line to kind of adjust the delay as you, and I guess that in turn depends on the channel characteristics. So I'm assuming what I said so far is correct. So if that's the case, then adjusting that delay, is that kind of done in the digital domain, or do you have like more of an analog sort of delay section there?
Yeah, so the delay itself, of course, is the switched capacitor circuit, right? And so controlling the delay is a question of controlling the clock phase shift. And so that happens, I guess you could say, in analog. But how you configure it happens from the digital, right? And so we have this sort of adaptive loop, right? That, looks at what the self-interference is, optimize the canceller, optimizes the weights of the canceller, which gives both the delay as well as the magnitude response, and then goes back and programs the canceller, right? And so this loop runs in digital, basically. but it controls the analog. And so that's the way we've been doing it. People have looked at sort of analog closed loop approaches. Of course, an analog closed loop approach will be faster, but it'll be less intelligent, right? So if you want to sort of use gradient descent and then even go to things like AI and machine learning on how to quickly adapt these cancelers to a changing environment, of course, that kind of stuff is hard to implement in analog, right? So I'd say we are believers in digital intelligence to program an analog canceller.
So I guess a related question would be like, generally the latency of these digital systems comes into play, and that kind of sets the minimum limit of the delay that you can kind of achieve. Is that correct?
Yeah, so the latency of how fast you can program these cancelers is important. Practically, you need to program them as often as the environment around the system changes, right? That's when something will change and you need to program it. And of course, so real life evolves more at best at the millisecond speed, right? So as long as you can get into the digital and converge these loops faster than, let's say, hundreds of microseconds, you should be okay. And that's definitely doable, right? I mean, it's not different from actually channel estimation in a regular wireless communication link,
right.
Except that here you have to do it also for self-interference.
So last question regarding that. So the data you showed I'm thinking in terms of the frequency of operation and bandwidth. Is that like the lower frequency numbers you showed, or is it possible to do something similar at millimeter wave frequencies? Or
yeah, so at lower frequencies, so at 1 gig thereabouts, we've been getting 40. I mean, there's some other newer work that gets to like 80, 100 megahertz. And so those are your typical LTE type bandwidths, right? Many
right.
tens of megahertz to approaching 100 megahertz of bandwidth. And that's what we've been striving for. We've done some work at millimeter wave as well, and we've gotten gigahertz of bandwidth there. And of course, what helps is that at millimeter wave, you don't need many tens of nanoseconds of delay, right? Because tens of nanoseconds of delay happens when a signal goes out, travel tens of meters, bounces off something and comes back. And at millimeter wave, those reflections are very, very weak, right? So at millimeter wave, the delay spread tends to be smaller. And so as a result, the bandwidths that you can achieve tend to be larger.
Okay, thanks.
Good. Okay, we can move on then.
Okay, so let me go to the final section of the talk, which is a little bit about systems and then emerging applications. And so, we've been active in demonstrating wireless links using these full duplex chips that we built. And so, we demonstrated a link actually at ISSCC this year, actually last year, this year also, honestly, and showing how with these circulators as well as these cancelers and software-defined radios, we can show full duplex operation live. We showed it across 1.5 meters just because the whole thing had to sit on a table. But with the signal to noise ratio that was measured, we could extrapolate the distance over which we could achieve still reasonable SNR. And so at least in that particular demonstration, you could get up to 100 meters of link distance and still get an SNR of 20 dB, which is enough to demodulate most modulations. And we've also done these types of demonstrations in collaboration with other groups. So this is some work with Jim Buckwalter's group. So he's been working on code modulation based self-interference cancellation. So we put our circulators together with his code modulation based cancelers. And demonstrated high levels of total cancellation north of 100 dB in collaboration with his group. And then again, we did a demonstration at this year's ISSCC in 2021, showing as much as a live 60 dB of suppression of a 20 megahertz OFDM QPSK signal, showing some of that adaptation live. And so showing that, you can get into the digital, configure the canceller parameters, and you can do all of that within microseconds of time so that it appears real time to sort of a user that's standing in front of it and maybe waving his hands in front of the antenna. And so then moving to translating this idea to arrays. So in an array now, what you need is you need some interface where you have multiple transmitters, multiple receivers, and multiple antennas, and you can now get isolation between any pair of transmitter and receiver antennas. And actually, that's where this topological insulator circuit that we talked about earlier actually shows some interesting possibilities. So we actually did a demonstration of a phased array using that, where you have these 16 circulators, you connect 4 of those ports to antennas, 4 ports to a transmitter through a power combiner to get the phased array combining, and then 4 ports to a receiver, again through a power combiner to get the phased array power combining. And so what we actually showed is, because you have programmability of the clock delay, you can get the programmable phase shifts you need to actually form beams that point in different directions. And because there's inherent isolation in that lattice of circulators, you can essentially get isolation between transmit and receive. And so you can get simultaneous transmit beamforming and receive beamforming at the same time in independent directions while having isolation between the two of them. And so we showed actually a 6-meter link, but with with high signal to noise ratio. So practically the link could be extended even to much longer distances. Again, we're just limited by this wire that has to connect the other side to this side just to synchronize those two radios. And showing as much as 44 dB self-interference suppression just in this antenna interface. The other nice thing about that topological insulator structure is that it can also, because it gives you true time delay, you can use that programmable time delay to actually do broadband beamforming. And so here I'm showing how you can actually do ultra wideband beamforming for impulse-like signals. So you have impulse-like signals coming in from a certain direction on these different antennas. If you hook up those antennas to the top and bottom ports, and you hook up receivers to the left and right ports, then again, you can program how the signal travels through the array to get any delay that you want. And so then you can align all these signals coming from a certain direction and hence form beams, but now beams not for narrowband signals, but for ultra wideband impulse-like signals. So now let me talk a little bit about emerging applications. And so one emerging application that we've been looking at is MRI. And so MRI today is time division duplexed. So, you have a powerful transmit pulse, and then you wait for the receive signal to come from the excited tissue. And, these are separated in time. But if you could actually do simultaneous transmit and receive MRI, where you're exciting and receiving at the same time, it has several benefits. One is it reduces the peak power that you have to transmit, because instead of transmitting a short pulse, you're transmitting throughout time. And so this has benefits where it reduces the heating of the tissue. In general, it makes MRI safer for the patient. And the second thing is that it also allows you to image tissues that have a very short relaxation time. So one challenge if you're doing it in time division is that so you have to switch off the transmitter and turn on the receiver. If the signal came in between before you could switch on the receiver, then you just missed that signal, right? So if you're simultaneously transmitting and receiving, you can actually image tissues that have a very short relaxation time. And so this is actually where these circulators also shine quite substantially, because essentially the non-magnetic nature of the circulator is actually very useful, because now you can put the circulator right next to the MRI instrument. You can't get magnetic circulators close to an MRI coil because it would mess up the magnetic field completely. And so here the non-magnetic nature actually allows us to integrate that circulator very close to the coil. And of course, over and above that circulator, you need cancelers to cancel the TX signal so that you can still get the receive signal. So a lot of what we have done for wireless can be translated to MRI and enable simultaneous transmit and receive MRI. And so, we've taken some initial steps in this regard. So I'm showing some experiments that we have run where we've built these circulators at MRI frequencies of around 60 megahertz, and then sort of integrated these circulators with a head coil and shown that you can get nice isolation and stable isolation even as the person removes his head out of the coil, basically. A few slides about some other projects. So we have this large NSF Power Cosmos project where we're actually building these types of wireless test beds which have emerging wireless capability, whether it's full duplex or millimeter wave or MIMO. And we're installing this test bed out in the city of New York, in and around the Columbia campus. And so this is meant to be a test bed that users can log into so that they can run their own wireless experiments and experiment with full duplex systems as well as with millimeter wave systems or massive MIMO systems. Another large project that I would highlight is the Com Center project, which is a center that's led from the University of California in Santa Barbara. This is looking at terahertz, so beyond 100 gigahertz. And so it's a multi-pronged center that is combining advances in devices with circuits and systems to enable operation beyond 100 gigahertz, to enable wireless links beyond 100 gigahertz. And so, stay tuned for interesting developments here. And then finally, just one slide, we've been working on electro-optical systems as well. So now going to optical frequencies, we've been working on circuits that enable FMCW LiDAR. So these are essentially phase-locked loops for lasers that modulate the laser in an FMCW fashion so that you can then build a LiDAR out of it. And so, we've actually built the support circuitry in CMOS, hooked it up to lasers, used our PLL to impart an FMCW modulation onto the laser, and then had you actually shot that laser out at a target, got the reflection back and imaged. And so this is actually some images that we've collected with this system of some gears using this electro-optical PLL and LiDAR system. So that's a very brief overview of some other directions that we've been taking. So that brings me to the end of the presentation. So hopefully what I'm motivated is that there are exciting things happening at the intersection of electromagnetics, circuits, and systems. They're enabling new forms of wireless communication, such as full duplex, millimeter wave, terahertz, etc. And this is an exciting direction. Of course, 5G is already driving a lot of excitement in our field. But then when we think about what 6G will entail, it's only going to be sort of more interesting directions for circuit designers, for electromagnetics people. And so, it's an exciting place to be. So with that, let me stop and open the floor to any final questions that you folks might have.
Okay, so I have one. This is Tom. Thank you very much, Professor, for a fascinating tour of, the amazing things you can do with time-varying circuits. But one question I have is, we have to, I've worked in some of these NPATH things over the years, and it's sort of disappointing that you have to, it seems historically anyway, you have to actually simulate the whole thing. And it seems like we're especially bad at, or let's say there's an opportunity for improvement of simplified analysis of time varying networks. And I'm a fan of conversion matrix analysis, which kind of unfolds the time variance into a multi-port time invariant circuit. But to get something interesting to happen, they have to be relatively high order. I think that's going to be easier to handle with symbolic algebra, for example, or other things. But I imagine a day when these time varying circuits can be analyzed in the way that we think about, phasors in college, entry level circuit theory, circuit analysis, right? Where we kind of got rid of the time domain and we even suppressed the Laplace domain and we're just doing phasors, right? Something simple, algebraic, like, it's just arithmetic. So what is happening on that front with regard to easy simulation, easy calculation methods?
No, this is a good question, and I think it's actually, I completely agree that this is an area that needs more attention. So these time varying systems are notoriously hard to analyze, right? And when I say analyze, there's two things, right? One is something that you can calculate out the response, right? And so conversion matrices is one approach, but conversion matrices, ultimately what you'll do is you'll code something into MATLAB and you'll get a response, right? Conversion matrices aren't amenable to getting a closed form hand calculated answer that's very simple. There's this kernel-based LTV analysis approach, which is how NPATH filters have been analyzed in the circuits and systems community. Some papers written by Bram Nauta and Eric Klumperink. It's exact, right? And it gives you the exact closed form answer, but it's incredibly tedious, right? Like pages and pages of, equations, right? And so that becomes intractable the moment it becomes even a slightly complex switched capacitor circuit. Like if you just add an inductor in series or something, any little thing that you do and that becomes utterly intractable. And then, there are some other things, right? So my collaborator, Andrea Alou, and we recently wrote a paper in Circuits and Systems, which is what we call a composite Floquet Floquet S parameters, so to speak, or Floquet parameter approach, right? Which it's in some sense in spirit similar to conversion matrices, but it's a little simpler.
Oh.
And so that's something that there's a recent paper. It's like just a couple of months out, and on circuits and systems in transactions and circuit systems. So you can take a look at that.
Yeah.
Right? There is some interesting stuff that was done by Shanti Pavan from India on an adjoint method. So that's actually a very simple method. It's just not applicable to all kinds of circuits. So there's this adjoint matrix method. But at the end of the day, I mean, it is true that all of these methods are either they don't give you closed form expressions, or they do, but only for certain specific cases. And so, yeah, I mean, I think there still needs to be a breakthrough in how these are analyzed.
Awesome. Thank you. I fully understand, and I'll take a look at that paper. Great. We have one question from Michael. Let me see. Can you unmute, Michael? There you go. Whoop. Sorry.
There we go. I think I got it now. Thank you. Thank you, Professor. It's just interesting talk. And you mentioned quantum earlier. Could you talk about something that you find interesting with the development there? You kind of touched on that in your talk, but maybe there's something you've done, or especially something you find interesting with that.
Yeah, absolutely. So, we've been working on circulators and isolators for quantum computing. And there, you want to build these circulators and isolators right at the qubit. So these need to be built at like fractional Kelvin, right? Like 0.4 Kelvin or something. And CMOS technology doesn't work in general, semiconductor technology, CMOS doesn't work at those temperatures because the carriers just freeze out. So we've been looking at how to build these same kinds of time-modulated reciprocal components using Josephson junctions, using the same device that's used to build qubits, basically. And so, Josephson junctions actually behave as parametric inductors, where if you pump them with a pump signal, then you get a time-varying inductance. And so there are some interesting things which are the duals of sort of the NPATH circuits. We're doing switched capacitor. Those tend to look more like switched inductor circuits. And so there's some interesting things that that we're working on, using Josephson junctions to build these kinds of non-reciprocal components for quantum.
Oh,
Well, thank you.
go ahead, Michael.
I was also thinking about the simulation of the machines, but I'm very interested to hear what the professor has to say about this. So I'll just quietly listen, because it's just a fascinating talk. And thank you guys. Thanks for doing this.
Absolutely.
You're welcome. Here, yeah, we invited the right speaker. We'll take all the credit on this. Well, Professor, I just want to mention, you're correct that in both CMOS you get freeze out, but it turns out in fully depleted SOI, which I happen to know a lot about because I've been working on it at the Global Foundries for some years now. People are getting surprisingly good results at cryogenic temperatures. I don't know if you've seen some of that Soren von Ionescu and
Yeah, and also Bogdan Stazuski, right?
Yeah.
They even have a startup, right? Equal One or something like that. No, yeah, definitely familiar with that work. And I think aside from just the devices working at fractional Kelvin, they're finding ways to actually implement qubits in CMOS, right? So no, I think that's an exciting direction. It's it's something. These are early days in terms of my group's activities, but I think that would be an interesting direction as well to pursue.
Cool. Okay, well, Akarsh, Tan, I think we're ready for closing.
Yeah, so just wanted to thank Professor Krishnaswamy. Thank you for doing this talk. It's definitely one of the best talks we've had, a very strong audience participation, both in terms of attendance and the questions asked here. So thanks again, Harish. Really appreciate you taking the time out to do this for us. Thank you.
Absolutely. Thank you very much for having me. And, thanks everyone for the extensive discussion. Definitely refreshing, especially for some of these online things. So, again, you guys are doing a fantastic job with this chapter and these events.
So Tan, you want to go ahead and introduce next month's talk?
Sure. Do you see my screen?
It's not quite full screen.
Oh, wait, I'm sorry.
Okay. All right. So for next month's talk, the speaker will be Mr. Tom McKay. He's actually our vice chair. He's a senior member of the IEEE, bringing over 35 years of experience in wireless IC design and innovation. So just tons of experience going from chip design to system design at multiple companies over the years. He has over, he has a master's in the University of Wisconsin-Madison and an inventor of over 15 US patents and patents pending. The talk will be held on July 21st, and it'll be between 6:30 to 7:45 p.m. The talk will be, the topic of the talk will be toward democratizing RFIC design. So in April 2021, the IEEE Solid State Circuit Society's Circuit Direction Initiative offered a webinar democratizing IC design, laying the foundation for an open source integrated circuit hardware design ecosystem in mixed signal 130 nanometer CMOS. Industrial radio frequency IC design builds on mixed signal design infrastructures by extending device compact models for required accuracy and by addressing multi-rate circuit simulation inherent in gigahertz carriers modulated at megahertz rates. Device compact model R extension relies on accurate linear categorization of test hardware with multi-gigahertz scattering parameter measurements. Open source VNAs now push into centimeter wave frequencies, and open source simulation software support harmonic balance and related RFIC centric methods. improvement in measurement tools, methods for IF extensions, modeling, simulator qualification, and design flow can extend open source IC design to wireless systems. The required collaboration roadmap includes open source centimeter wave BNA architecture supporting modern self-calibration method, silicon on wafers, OS BNA calibration elements, simulator-based device modeling, simulator test cases, and design flows consistent with constrained open source tools. Informed by over 35 years in gas and silicon RFIC technology, product advanced development and design, the authors outlines one path to a healthy open source RFIC hardware ecosystem. So please join us next month for this talk. Thanks.
Before we break away, I just I messed up the full scale share screen, so I'm just going to do it again. I just wanted to add a few words to what Tan just said. Just give me 1 second, please. And can you guys see the right screen right now? Is it?
I see. Yeah, we see the screen.
Okay, let me just go to full screen. Just want to make sure. Can you? Is it the right screen or?
Yeah, it was right. It was fine.
Okay, I just wanted to mention that this is a discussion that a lot of us have been having about the higher entry barriers for companies in terms of the kind of equipment, the level of investment needed, and even for individuals trying to break in terms of the cost of education. So this is a pretty important talk, and I hope you guys will all register and be here. Because this is something that a lot of us in societies like the IEEE are starting to think about, like how we can get this resources for individuals and companies out there and lower the kind of barriers that exist. So this should definitely be a very interesting talk. So look forward to seeing all of you guys there. So once again, I just wanted to mention IMS and the virtual events. So the links up there on the screen, ims-ieee.org. If you haven't checked it out, please do so. And of course, please support us by becoming a member. The links for IEEE, MTTS, and CAS are listed here. Of course, if you have to pick between MTTS and CAS, please pick MTTS. I'm just kidding. So with that, we've come to the close of our talk here, and we hope that you'll join us for next month's talk, and we'll go from there. Thank you very much. Thanks again to the speaker, and we'll see you all next time.